This lesson is going to be about force diagrams, and learning targets to be able to model the forces acting on an object. So anytime we're representing the forces acting on an object, we're going to draw something called a force diagram. And the objects are always going to be represented by a box. So we're always going to draw that. You might see some people that draw a dot. You might see that sometimes and have arrows coming out of it. That's fine too. We are going to draw ours with a box. It makes it a little bit nicer just because if there's multiple forces, we can draw both of those on that box. And so the other part of this is that the forces are represented by arrows, and the arrows are going to show us how strong is the force and in which direction is the force acting. And so the strength of the force is the magnitude. It's another word for strength. And so if I have, for example, two forces acting downwards and I have one is longer than the other, this one would be the strong force. It has more magnitude. And both of them would have the direction of downward. And the way that these would match up onto our box is we would draw them with the tail touching the box, and then the arrow would go outward from there. Now we would always label this too, and so you're going to see in the next slide that this is the force of gravity is going to be the downward force. And so we put our label on there, and we can also label the magnitude of the force, the strength of the force, with an actual label, with a number and newtons on there. And so when we have actual numbers for the magnitude of our forces, we would add those in there. But this is how we use our force diagrams, the boxes and the arrows, in order to show the forces onto an object. So when we're identifying forces, every time that we're trying to identify the forces acting on something, we are going to draw a net force diagram. And that's going to start with a box representing the object that we're actually drawing the forces of. And we're going to ask ourselves 4 questions. The first one is it on Earth? Because if it's on Earth, then we know that the force of gravity is acting on it. Right? So the force of gravity is going to pull us back down towards Earth. And so the way that we're going to represent this on most objects as they're on Earth, unless a very special situation comes up, is we're going to draw the force of gravity acting downward. And we're going to label it F grav. And then we need to ask ourselves, is it being held up by something? Is that object being held up by like a table or the earth, or is it being held up by the floor? Is it being held up by the roof? Because if it's being held up by something, then we have the normal force acting on it. The normal force is going to act perpendicular to the force of, or the actual surface. And so like if we had a table, right, we had like a ball sitting on top of the table, we know it's on Earth because so it has gravity acting downward on it. Well, the table is also acting back upwards on the ball straight out of the table. And so if we have this object being held up by something, I know that I have the normal force acting upward on that object, F norm. Then we ask ourselves, is this object being pushed? If it's being pushed or pulled, we know that there's a force being applied onto the object. And so, for example, if I was going to push this baseball over to the right, I know that I am applying a force to the right. And the applied force can either be left, right, it could be up, it could be down. It's really what direction are we pushing that object or pulling it. And so then we're going to draw that force in as force applied. And then if it's rolling, sliding, etc., like for example, if I had I don't know, a book push across carpet or something like that, that book's not going to go very far. We know that friction's acting onto it. So if something is rolling, sliding, then we're going to have friction acting on that object. And friction is always going to oppose motion. So for example, if an object is moving to the right across a rough surface, friction is going to move or is going to act to the left. In this case, if our ball was rolling to the right, friction would be acting back towards the left. And there can be a lot of different varying levels of friction. This would be force of friction. There can be a lot of different levels of friction. Obviously, you know that like a ball rolling across the floor is probably not going to have as much friction as a book sliding across the floor. And so you got to take that into account when you're drawing your force diagrams. But the force of friction is always going to oppose motion. We know that based on if it's rolling, sliding, or something like that. So this is how we identify forces and get our force diagram set up. And so if we have this situation here, a book is at rest on a tabletop, I can ask myself those 4 questions to try to figure out what forces are acting on this object. Well, I can ask myself, is it on Earth? I would say yes for this one. And so the book has the force of gravity acting on it, so that force of gravity is going to act downward. Force of gravity. Right, now I ask myself the second question, is it being held up by something? Well, it's on top of a tabletop, and so it is being held up by something. And because it's at rest, I know that these forces are balanced. It's not accelerating, it's not doing anything, it's balanced. And so I draw a force, the normal force, because it's coming straight out of the tabletop. That is the same length as my force of gravity, so I know that they are balanced with each other. They are equal in magnitude and they are opposite in direction. One is pointing up and one is pointing down, but they're the same length arrow. I can ask myself, is it being pushed, pulled by something? And the answer is no for that one, so I'm not going to draw an applied force anywhere on here. And it's not sliding, rolling, and so I'm not going to draw a force of friction. So this would be my final force diagram for this situation. So if I had this problem right here, I could draw myself a little picture, the classic tree trick, just keep drawing V's, and eventually you end up with somewhat looking like a tree. My aunt taught me this one time and it changed my drawing world forever. You probably can't believe that based off of the tree that I'm drawing, but if you keep drawing V's at the end of all of your branches, you will eventually get something like a tree. I'm not going to finish this side because we've got things to do. So I have an egg falling out of a nest. So I have my little nest out here at the end. Got my little baby bird. And I've got an egg that's either jumped out of the nest, got kicked out of the nest, or otherwise. And so this egg is free falling from nest to tree. I'm not going to think about air resistance, diagram the forces acting on the egg as it's falling. So I draw my box to represent this egg. And I ask myself the first question, is it on Earth? Because if yes, then we do have the force of gravity. I ask, is it being held up by something? Well, no, it was being held up by a nest, but since it's free falling, it's not. It's just in the air, it's falling down. And so I am not going to draw my normal force in here pointing upwards because there's no surface that's pushing back on this thing. I ask, is a force being applied onto it? Well, as long as the mother bird didn't throw it downward, it just kind of pushed it out of the nest and then it fell downward, I'm going to say that there's not an applied force acting on this object unless it, as long as it didn't get thrown down or it's being thrown up or, something like that. But it's just falling, so there's no applied force on this object. And then I ask, is it rolling, sliding, etc., something where friction could be acting onto it, and it's not. So it's not rolling or sliding across the surface. If we were counting air resistance is a type of friction caused by the object moving past the particles of air. And so that would be an example of friction that would act upwards, but we're told to neglect air resistance. And so we're not going to draw any other forces, and this would be the final force diagram for this situation. And so if we looked at this one, the last one, a rightward force is applied to a book in order to move it across a desk with a rightward acceleration. Consider frictional forces, neglect air resistance. Diagram the forces acting on the book. So we ask ourselves 4 questions. Is it on Earth? And the answer is yes. And so we would draw the force of gravity, and we would label that. And so then we ask, is it being held up by something? Well, it's on top of a desk. And so I'm going to say that yes, it's being held up by the desk. And so this would be F norm. Is it being pulled or pushed by something? It is a rightward force is applied to a book in order to move it across the desk. And so I'm going to say that there is an applied force applied to the right. That's what I'm going to draw that in as. And then I ask, is it sliding, rolling across a surface? And this I would say yes, because it's moving across the table. And this problem specifically says to consider frictional force. And so I'm going to draw a frictional force in here. Now the question is, how big do I draw my frictional force? Well, we can look back through the problem. Rightward force applied to a book in order to move across the desk with rightward acceleration. Bam, right there. Rightward acceleration. This is my key word here, because remember that if I have an acceleration, that means that there is an unbalanced force acting on this object. And so what that is going to tell me is that my force applied is bigger than my force of friction. That's what I think. I say, okay, there's a rightward acceleration, so there's got to be an unbalanced force to the right. That means that the force to the right must be bigger than the force to the left. And so I know that since it's moving right, friction is acting to the left, but since it's accelerating to the right, I know that friction is less than the applied force. And so I can draw my force diagram in here. This asks us to neglect air resistance. It probably wouldn't be very much if it was a book across the desk, because I don't think air is going to slow that down a whole lot. But this would be our final force diagram. And so I hope that by asking yourself those 4 questions, is it on Earth? Is it being held up by something? Is it being pushed, pulled, or a force being applied to it, or is it rolling, sliding, something across the surface. You should be able to figure out how to draw a force diagram of an object, and then in the next video, you're going to figure out how to find the net force of an object.